In 3.2, we are going to play around a little with the exponential functions. And by definition, that is any function that is written as y equals a raised to the x power, where a is a constant. And we will also just fiddle with e. So let's talk first about e and just refresh your memory about what that number is. Now, you might remember from pre-calc that E is referred to as Euler's number, named after the mathematician Leonard Euler, but it's spelled E-U-L-E-R. And here is one of our definitions for how we can go about discovering E. You might remember that E is irrational, just like pi, and we will look at where we find those values or where that number is on our graph. So if we're looking at our calculator, there are two places where we can find E. There's one that I find less practical, and that is right here where we go to second division. And I'm only doing that just to show you where it is and then to show you what that number is, 2.718, and on and on and on. The one that we are going to be using with frequency is second and then above the natural log button. So second E gives you E and then the caret. Super useful. Then we could say E squared or whatever we want. So here's the second thing. If we put that limit definition, the expression 1 plus h all raised to the 1 over h in our calculator, except I'm replacing my h's with x's, and then I go to second table set, and I start my table at 0 and my delta table at, I don't know, like point that. And then I go to the table to see what that looks like. Obviously error, but we can see that the closer we get to 0, if we let that h approach 0, our numerical value, our limit, is going to approach E. So you'll see that a lot of what we're doing in this unit is a little bit of a discovery. So I would not write everything down, but I don't know, it's kind of nice to appreciate the proof behind what these derivatives are. So play along with me and I'll try and keep this brief. So let's start with this part. If we're given this exponential function, let's use our limit definition to find f prime of x. So my hope is that you would just type in our limit definition and it would look like this. The next piece I want you to be comfortable with is this part, where we know that a to the x plus h, if I add the exponents, that would have been the same thing as a to the x times a to the h. We're sort of going in the reverse direction that we typically do. But we know that to be true. That's useful because we can then see that both of those terms in the numerator have a to the x in common, so we could factor it out. And we would have this. Now, this is our sort of messy solution to what that limit definition is. But here's one thing that I think is super neat. You'll notice that the derivative of a to the x includes the function itself. What does that mean? I just mean that this a to the x, its derivative is a to the x times the rest of this, meaning I could write this just like so, since this a to the x right here doesn't really have any bearing on h approaching 0, so I could just pull it out and say that it's a to the x times this business. So our end game is saying this derivative, we're going to clean this up in a second, folks. This derivative is itself times this little piece. So we're going to play around with this little piece. So there's this neat question of saying, when would this function actually equal itself? Meaning, depending on what my a value is, when would this, for what a value would this equal 1? That's what that green question is saying. For what a would the derivative of a to the x equal a to the x? So let's do some quick math and figure out what value that would be. So I would just start off by setting that one expression equal to 1, and then we'll tag on the h approaching 0 next. I'd multiply both sides by h. I'm trying to get that a by itself to figure out what a value is going to make that expression equal 1. Next, we would just add 1 to both sides. And then we would raise both sides to the 1 over h just to get a by itself. And we notice that that gives us this expression. So we know that it's the a that would equal the limit as h approaches 0 of 1 plus h all raised to the 1 over h. Well, what a value is that? It's e. So our discovery, if you followed that, is that the derivative of e to the x is in fact e to the x. Let's also just appreciate that from a graphical standpoint. We know that the graph of e to the x is exponential. Looks like that. Goes through the point 0, 1. Fine. So here we know that those slopes are they're positive, but they're little babies. And then as we continue, we see that our slopes are increasing. So if we were to sketch the derivative, it would lie flat on top of the original function. Actually, write this out with the class, but I understand it's a video. Let's keep it going. If you are interested in finding out how we determine the derivative for any exponential function a to the x, pause it here and follow along. And you will identify that these are the two derivatives for this unit. That the derivative of a to the x is itself times the natural log of a, and the derivative of e to the x is just e to the x. We're going to do some nice friendly problems just to make that clear. I also want you to be comfortable identifying that if I used this same formula with e to the x, it would look like this. E to the x times ln of e. But pre-calc, what do we know ln of e is? That's log base e of e. That's 1. And that's how we end up with just e to the x. So don't do that. Just know that the derivative of e to the x is e to the x. What would our derivative of 6 to the x be? It would be itself 6 to the x times the natural log of 6. What would the derivative of 19 to the x be? 19 to the x times the natural log of 19. Here are some problems. Why don't you pause it? And in a minute, I will post the solution. And these are the solutions.